In our previous discussions on limits, we talked about the idea of having an infinite limit. Two examples. The limit as we approach 2 from the left, of 1 over x minus 2. Same function, same number. What happens as we approach from the right? Limit as x approaches 2 from the right, 1 over x minus 2. What's happening as we approach 2 from either side? What's going on at 2? There's not a hole in this graph. There is a problem, but it's not a hole. It's an asymptote. But that means we can get as close to having an asymptote is like being with your significant other at your parents' place. You can get as close as you want, but no touching. So I can get as close as I want to 2 from the left. I just can't get there. I can get as close to 2 as I want from the right. I just can't get there. So what happens is we get closer and closer to 2, the y values. Pick a side. Tell me what's going to happen. Draw the graph. Make a table. You have methods in front of you to deal with this. Tell me what's going on. Gesundheit. Yes, please tell me what's happening. Because our graph looks like that. If you don't have this picture, but instead have a picture where it looks like the asymptote is at 0 and everything is shifted down, that means you forgot to put parentheses around your x minus 2. Please be careful. So what I have here is a limit whose value is infinite. An infinite limit. That's not really a number. It's an idea. We're descending without bound. We're growing without bound. What is this an idea of a limit at infinity? Let's allow that decrease without bound and increase without bound. Instead of referring to y, refer to x. I just realized I did these on the wrong side. The one on the left is going to positive infinity. We're going off to the right. Should have put the minus sign on the other side. We won't worry about that for right now. I have a limit as x goes to infinity. Again, to infinity isn't a number, so it just means what happens as x gets bigger and bigger and bigger and bigger and bigger without bound. Here I have the limit as x goes to minus infinity. It's not a number. We're just going left, and we keep going left and don't stop going left. So if this is what's happening to my x values, what's happening to my corresponding y values? So that means as x approaches infinity, our y values are going to keep getting bigger and bigger and bigger. That's not what's happening in that graph. What do you see? It looks like it's getting closer and closer to 0. Does the same thing happen on the left side? It looks like it from the picture. Whether I go off to the right to positive infinity or to the left to negative infinity, these graphs seem to close in on the y-axis. If I were being pedantic, and you know me, I'm a math person, therefore, of course, I'm going to be pedantic, I could say we should have an epsilon delta idea. I don't want to do it formally. Let's try and ad-lib this with the picture. Remember, we had that horizontal strip, and then we would say, oh, you need to be within this close. Well, now I'm saying we have this horizontal strip above and below 0, and you need to be far enough out when we go to positive infinity, far enough to the right. When we go to negative infinity, far enough to the left. So instead of saying you need to be within a particular vertical strip, I'd say you need to be bigger than some number as we go to positive infinity, or smaller than some number as we go to negative infinity. So I can still do this in formal epsilon delta language. I'm not ever going to. I'm just going to say, well, how far out do I need to go? Depending on which direction I'm going. This is the linguistic version of my epsilon delta idea. The limit as x approaches a of f of x equals L means x is arbitrarily close to L. That's our epsilon. By making x arbitrarily close to a. That's my delta. You can get as close as you want to L. You just have to get really close to a to do it. So if I think of translating this idea to infinity, I change this second piece. If I want to get arbitrarily close to L within some distance, I need to have x get really, really big. Now, really, really big depends on the function we are looking at and our epsilon. In some cases, I might have to go out to x equals 1,000. In some cases, I might have to go out to x equals 100 million. It depends on the function. In some case, I might just have to go out to x equals 2. If I change that plus infinity in the limit here to minus infinity, what's going to change in this underlined phrase? Okay, I have a problem with using the idea small. Because if I tell you a number is arbitrarily small, most people think it's close to 0, right? An arbitrarily small number is like 0.00003 or something. But arbitrarily small should mean that way. So I'm just going to write arbitrarily large and negative. That's the change that goes with making this minus infinity. When this is the case, when I have a limit as I go off to positive infinity or off to negative infinity, then I'm getting arbitrarily close to some fixed value. Let's consider a line. For the example we were just looking at, we could consider the line y equals 0. Because we looked at our 1 over x minus 2, and we said, oh, as you go out to the right, you get 0. As you go out to the left, you get 0. Let's think about the line y equals 0. Again, 1 over really big number. 1 over 180 million. Is that 0? It's really, really small, but it's not actually 0. 1 over negative 3,875,000,000. Is that 0? But it's really, really close, isn't it? So again, we're approaching this line, y equals 0, but we're not actually touching it. That's exactly the same description we used talk about the line x equals 2. So this line we'll call it a horizontal asymptote, as opposed to the vertical asymptote we were just dealing with. But please notice, a horizontal asymptote means at least one of the limits, either to the right or to the left, is L. The function we were dealing with, 1 over x minus 2, it was on both sides. Think back to your algebra class. Can you name a function that only has an asymptote on one side? Got to do the math dance again. What's this graph? Huh? An exponential function like e to the x. The graph of e to the x looks like that. That swoop there. And as we go off to the right, that gets bigger and bigger and bigger and bigger. So here's a case, Chloe, here's a case where I would have the limit as we go to infinity is infinity. Because that right side's just going to keep shooting up. Whereas if I go and put in more and more negative numbers, I get 0. That is looks like a theta like that. Fix that. There we go. Which means I have a horizontal asymptote at y equals 0. But I only have that asymptote on the left. Trig class. There are functions that have different asymptotes on different sides. We've already talked about one of them. I showed you its picture in the back of the book, in the reference pages. See if we can find it again. Grab your textbook. Reference pages in the back of the book have these lovely little bluish gray edges. If you have your physical textbook with you, if you have your ebook, you can look it up there too. In those back marked reference pages, that was a picture of a graph with 2 different asymptotes, the right versus the left. What was it? Ah, the arctangent function, the inverse tangent function. Has a horizontal asymptote on the right at y equals pi over 2, and a horizontal asymptote on the left at y equals minus pi over 2. So we have to be careful and make sure that we're talking about asymptotes on the correct side. Now, there is a distinct advantage to something like 1 over x minus 2. Isn't it? So as soon as I know that there is an asymptote on the right for a rational function, I know I have the same asymptote on the left. $64,000 question. The hell's a rational function? What's that mean? Colin. I need to be a little bit more general of a description to try and nail this down. But yes, something like 1 over x, like 1 over x minus 2, but there are millions of others. What's the characteristic that makes a function rational? That's what makes a number rational. A rational number is one whose decimal expansion either repeats or finishes. But even there, that's not usually the way we write rational numbers. When I write a rational number, I'm using the root word of rational, which has nothing to do with Mr. Spot. Ratio, a fraction. A number that is rational is a number I can write as a fraction. 7 over 13. A half, 2/3. Notice 2/3 has an infinite decimal, but it repeats. 1/2 has a terminating decimal. If you can't write a number as a fraction, then it's going to give you a non-repeating, non-terminating decimal. The square root of 2 is 1.414, that keeps going forever, never repeats itself. Pi, 3.141592653, keep going. For the record, March 14th last year, no, sorry, this year, March 2025, back in spring, we had a pi competition. How many decimal places of pi do you know? I know 10, I've never needed more. The winner was able to recite 150 from memory. There's a challenge for you all this coming March. Yes, I am most of the time too. So a rational function is a function that looks like that rational idea, but the top and the bottom are polynomials. So something like this. That is a rational function. So is that. So is that. So these are all examples of rational functions. That means that each of these has at most one horizontal asymptote. How do I find it? If I set the denominator equal to 0, that will give me places where I'm dividing by 0. That's not permitted. That gives me the vertical asymptotes. So vertical asymptotes occur wherever my denominator is 0. Hold that thought. So, by the way, G and H have no vertical asymptotes because the denominator can never be 0 in either of those cases. F, on the other hand, has 2 of them. Take x squared minus 3, set it equal to 0, you get plus or minus the square root of 3. If I want to find the horizontal asymptote, I want to take the limit as we go off to infinity. So really, if I want to know where does this have a horizontal asymptote, I want to compute this limit. Now, for the moment, I'm going to make this claim. For a rational function, it's just easier to deal with going to positive infinity. Because at best, I will get one asymptote. So if I get one on the right, I automatically get it on the left. And I don't have to worry about the negative signs anywhere. I want to save myself the headache. I'm going to just do the right side. If I try and use the limit laws, I'm going to get infinity minus 1 over infinity squared minus 3. And that doesn't mean that is a useless expression. It's another indeterminate form. So if I were to say, okay, I'll take the limit of the top, the limit of the bottom, separate from one another, and then I'll try and substitute. Infinity is not a number. I can't substitute like that. So really, I'm stuck because this somehow kind of goes to infinity over infinity. And that's another one of our indeterminate forms. At this point, I would curse thoroughly. So, why? Why? Again, I'm not sure why that works. So let me see if I can justify that. She suggested that I go through and look at just the powers and look at where's the highest power. But I'm not sure I understand why that's going to work. So when I had an indeterminate form look like 0 over 0, what did I do with it? I could factor and cancel. Or like with that square root of t squared minus 9, t squared plus 9 minus 3 thing, I could multiply by some expression. I have an idea. I'm going to multiply. I'm going to multiply by 1. If I multiply by 1, I'm not changing stuff, right? But I can write 1 however the hell I want. The highest power in this problem is an x squared. So I'm going to make my 1 look weird. Here's my 1. Oh, something over itself, that's equal to 1. And I know I don't have to worry about the dividing by 0 routine because x is going off to infinity. I am as far away from 0 as I can get. Well, let me multiply through here. Hey, wait a second. Wait a second. This top expression, x over x squared, that simplifies, right? That's just 1 over x. Now here is the helpful statement that will allow me to evaluate this. A helpful statement in mathematics is called a lemma. We have theorems and axioms and statements and proofs. A lemma is a thing I can demonstrate that helps me out. Think about 1 over x to a power as that power is positive. One over x squared. Oh, wait a minute. Positive power. I need to make one more containment. Positive power p bigger than 1. Why bigger than 1? Not bigger than or equal to 1, actually. What happens when you take the square root of a big number? Square root of a big number gets smaller. Oops. But 1 over x to the p is 1 over a big number. 1 over a big number is really, really small. And as the bottom gets bigger, the whole fraction gets smaller and smaller. 1 over x to the p goes to 0. What does that tell me up here? Well, now I can use my limit laws. The limit of a quotient is the limit of the top divided by the limit of the bottom. As long as the bottom works out to be not 0, this is fine. Separate subtractions. Limit 1 over x minus limit 1 over x squared, both as x go to infinity. Separate subtractions here. I have the limit of 1 minus, what can I do with a 3? 3 is a constant multiple. I'll pull it out front. And now I have 3 different instances where my lemma comes into play. What's the value of this limit here in the bottom? Just this one. That looks like this. That's a 0. Here, that's the same limit, so that's also a 0. Here, 0. Which means when I actually evaluate this limit, I get 0. Now, in general, What the is that? I'm going to run the screaming. No. Hang on. These are polynomials where these A's are numbers, and I'm just using the subscript to keep them with the right power. So AN is the number in front of x to the n. A2 is the number in front of x squared. A1 is the number in front of x. AN minus 1. So if this started with a to the 7th, then AN minus 1 would be A6 going with x to the 6th. So the top is a polynomial whose highest power is n. The bottom is a different polynomial whose highest power is m. That's the only difference. This is a rational function. That means I'm going to play the same trick. I'm going to divide by 1 over x to the highest power. The highest power in this problem is one of these two. Whichever one is bigger, n or m. Maybe they're the same. Maybe we have a tie. Like g of x has a tie in it. If the power on the bottom is bigger than the power on the top, then the limit as x goes to infinity of f of x is 0. If the bottom has the highest power, it's going to win, just like our example that we just did. If they're the same, then the limit as x goes to infinity of f of x will be an over bn. Why did I change that from an m to an n? Because they're the same. If the top is bigger than the bottom, then I don't actually have an asymptote. My limit is either positive infinity or negative infinity. And we'll have to figure out how to tell which is which based on the signs, positive or negative, of the coefficients involved. But since I don't have an asymptote, it could be different when I go to positive infinity versus negative infinity. I'm pretty sure in your algebra class, you should have talked about horizontal asymptotes for rational functions exactly this way. Just compare the powers on top and on bottom, exactly as you suggested. And the place where the higher power is, that wins. If the top has the highest power, we either blow up to infinity or blow down to minus infinity. If the bottom has the highest power, we're going to 0. And if they're tied, just take the ratio of the coefficients. So literally, all I have to do is say, hey, look, it's an x squared on the top, it's an x squared on the bottom. Those are the same size. Everything else is irrelevant. I'm done. The coefficient 3 and 5, that's all I need. If the top is bigger, we had an example written down earlier. This value is either going to be positive infinity or negative infinity. So I need to know when x is really big, is the resulting number positive or negative? When x is really, really big, x cubed is so much huger than x. X squared is so much bigger than 4 that I can play the same idea and I can ignore everything except the leading pieces. There. Wait a minute. 2x cubed over x squared would simplify to be 2x, right? This should be going like this, because that's what the line y equals 2x looks like. It goes up as we go off to the right. No, if I just write infinity, it's assumed to be positive. I'm just emphasizing it here for the moment. Those of you in computer science, cybersecurity, at some point later on, we'll talk about algorithmic complexity and relative sizes. And later on in this class, we'll talk about my buddy, the Marquis de l'Hôpital, and his rule for dealing with indeterminate forms. And there turns out to be a whole lot more here, because what we really want to know in terms of what happens as we go off to infinity isn't really about just taking the limit of some function for the hell of it. I'm thinking about larger and larger data sets that I'm doing analysis on. And I'm saying, okay, my program is going to take some function of the size of the data amount of time to work with. How big is the hard drive on your machine? You've got a computer in front of you. Any idea how big the hard drive is? If you got your machine from here, that's a university laptop, it's 500 gigabytes. Okay, for the record, how big is 500 gigabytes? You have any idea how big that is? That's about 600 copies of the Avengers Endgame movie. You could fit 600 movies on your laptop. That's a lot of information to go through, isn't it? If I said I need to scan a laptop to see if a file is on it, and that laptop is full, how long do you think it's going to take? A while, right? If I take the number of phone calls made in the United States today, that's not measured in gigabytes. That's not measured in terabytes. That's not measured in millions of terabytes. Tera, peta, exabytes. The amount of information from 1 day's worth of phone calls in the United States is 2 billion hard drives. How do I search for a phone call? How long is it going to take me to search for a phone call? If I work for the justice system and I need to know, hey, did my perpetrator call somebody? How do I find out? I'll be here for a month, if not longer. Can I make the algorithm faster? Can I make it better at looking for certain things? I need to look at what happens as the number of data points I have gets really freaking huge. A lot of cybersecurity depends on the fact that as these numbers get bigger, things take longer. If you have a password that is 8 characters, which is the minimum one required for your Seton Hill logon, I can break it in about an hour and a half with nothing more than a brute force attack. If it's 16 characters, it'll take me a little over 3 months to break that password. Just by doubling the number of letters. What happens as my passwords get bigger? So why can I get away with making your ATM card code only 4 digits? Here's one type. More on that in the algorithms class. Questions? What if my function's not rational? As soon as I see that square root floating around in there, I know this is not a rational function anymore. So I can't just compare highest power, lowest power in the same way. But let's start with that idea. If I were to just look at the highest and lowest powers, the highest power on top, it's x squared, but it's under a square root. Doesn't that just make it an x? So wait a minute, the top and the bottom are equal. But how do I show that I should be able to do the same thing? I got to go back to that 1 over x idea. So I'm going to multiply by 1 over x on top and 1 over x on the bottom. But in order to deal with the square root, I'm going to change the way I write x on the top. Instead of writing 1 over x, I'm going to write 1 over the square root of x squared. Now you may be going, why the hell would you do that? Because when you multiply or divide square roots, you can combine the things under those square roots. So when I multiply on top here, I actually get 2x squared plus 1 over x squared, all under that square root. And now things get nicer. Now I play the game with all the limit laws. I have a continuous function when x is far away from 0. I can do direct substitution here. I don't know how to substitute infinity. I get to use my lemma. What happens to the 1 over x squared inside the radical there? Oof. What happens to the 1 over x on the bottom? Well, 5 over x. Same thing. 5 divided by something really huge is 5 zeros. That's still 0. And so I get the square root of 2 over 3. Now you might look at this and think to yourself, hey, isn't that just the coefficients up there? And the answer is yes. This time, watch what happens if I change that limit, and instead of going to positive infinity, I go to negative infinity. I'm going to do almost exactly the same thing. I'm going to multiply by 1 over x over 1 over x, and then I'm going to write that weird. 2x squared plus 1 over 3x minus 5. On the bottom, I'm going to leave it as 1 over x, but there should be a minus sign there. Don't lose the minus sign. On top, that's wrong. This is incorrect. Why is that incorrect? There's a really sneaky thing about what happens when you write a square root like that. That symbol, that radical symbol, means the positive square root. And our x's are negative numbers. So in this fraction, the bottom is negative, but the top isn't. That's not 1 anymore. You can't do that. You're only allowed to multiply by 1. You can't change it arbitrarily. I need to make the signs match. So in order to make the top sign match the bottom sign, there needs to be a minus there. You sneaky mother. It's not the calculus that's the problem. It's the freaking algebra. But now everything else behaves exactly the same, except I have a minus sign floating around in the whole problem. I'm going to take that minus sign and put it in front. Right here. Limit x goes to minus infinity. Negative root 2x squared plus 1 over x squared over 3x minus 5 over x. Which means, with the exception of that extra minus sign, everything happens just like before. And that means this 1 over x squared becomes 0 again. This 5 over x becomes 0 again. And I get negative square root 2 over 3. It is absolutely correct for this function to have a different asymptote on the right than it does on the left because it's not rational. That square root makes it an irrational function. And that means that I can have a different thing on the left than I have on the right. Will I always? No, but I can. Please note, this means I can resolve an indeterminate form that looks like infinity over infinity as I resolve the indeterminate form that looks like 0 over 0. I can do the same thing if I look at subtractions. Does it make sense to say infinity minus infinity? Doesn't make a damn bit of sense. But consider that. When x is really big by comparison to 1, x squared plus 1 is really close to x squared. When I pick really big x values, what's 100 squared? 10,000. 10,000 is really close to 10,001. A million squared is 10 to the 12th, a trillion. Adding 1 isn't going to make that much of a difference. So that means this is just about x. X minus x should be 0. But that's infinity minus infinity. I can't do that. So somehow, again, I need to reconcile this infinity minus infinity and make it from an indeterminate to a determinate. I'm going to multiply by 1. The one I multiply by is going to look like this. What the? Notice it's just like that expression, but I changed the minus in the middle to a plus. This is called the conjugate expression. Comes from my factoring ideas. I have a minus b times a plus b. That's a squared minus b squared. When you multiply this out, some really nice stuff cancels in the numerator. And the resulting limit is one I can actually do. Infinite limits are just a way of saying that our function grows without bound. Limits at infinity ask what happens as we, our x values, grow without bound. Tomorrow is question and answer day. You should be bringing me lots and lots of questions. I will see you all then. But my goal is to stay up here If you have a question, rather than me wander from group to group and answer the same question multiple times, I want you to ask it. Please ask it. If one of you has that question, I'm sure a bunch of you have that question. See you tomorrow.